Welcome back to part 3 of chemical equilibrium. Calculating equilibrium constants is something that's very important in most areas of chemistry, especially like biochemistry and chemical engineering. What we're going to do in part 3 is we're going to start using numbers and calculate some of those equilibrium concentrations, and we're going to use the experimental concentration measurements to figure out what you are going to get when you get done with the reaction. And so we're going to use something called an ice table. And forgive me if I break out into ice baby, because that's what I think of every time I use this. So the most direct way of finding equilibrium constants is to measure how much you have of the reactant and products in a mixture. And you can do that experimentally, obviously, and you can monitor the depletion of the reactants or how the concentration in the products increase. It depends on which one's easier. But the mixture could have different amounts, okay, even if the equilibrium constant is the same, as long as you keep the temperature the same. Okay, I know that doesn't sound quite right, but you're going to see when we kind of plug those numbers in how that works. So remember stoichiometry, and that's how the reactions work based on molar ratios. Equilibrium concentrations will also follow that, and that is a killer clue, because if you have a balanced chemical equation to go by, then, and you know one of the concentrations, you can figure out the concentrations of the other thing that goes with that. Like if you know the reactant and you know the proportionality of them molar ratio wise from a balanced chemical equation, then you can also know what the concentration is if you have another reactant. And the same thing with the products. So you use the changes in these concentrations of the materials so that you can determine the change in all the other chemicals. And so as we work through these equilibrium constants, I'm going to kind of key you in on which type we're looking at, okay? We're going to start out with the easiest one where you're given all the concentrations. And if you're given it'll say at equilibrium, okay? These are the concentrations. And then if you know that, then all you have to do is plug that in and you can figure out what the constant is. If you know the constant, then you can plug it in and figure out what a concentration is if you don't have it. So we're going to look at those in a minute. And this is something that I do when I'm working a problem for this, is once I figure out what the concentrations are, I'm going to write the concentrations that I know underneath the chemicals in the reaction. And that just kind of keeps me, I remember what's reactants and products, and I remember, okay, so this is going down and this one's going up, because remember, your reactants are going to go down typically and your products are going to go up in concentration. So 1 liter, and that's important, especially if you're doing, because you got to do molarity, right? So if it was 2 liters, you'd have to take that into consideration. But 1 liter of an equilibrium mixture at a high temperature, and you don't care, was found to contain 0.172 moles of phosphorus dichloride, 0.086 moles of chlorine, and 0.028 moles of phosphorus pentachloride. And it just wants to know the Kc. So this is the example of you're given all the concentrations. Since you're given all the concentrations, all you have to do is write what your general equilibrium expression is. In this case, it's really easy because they're all 1 mole. So you don't have to worry about raising anything to a power. So you remember that it's products over reactants. So it's going to be PCl3 times Cl2 divided by PCl5. Lots of ways you can combine chlorine and phosphorus. All right, and then since I have numbers, I can plug those numbers in. 0.172 molar times 0.086 molar divided by 0.028 molar. And I know some of y'all are kind of anal about this, okay? Why am I writing molar? Because it's telling me I've got 0.172 moles in 1 liter. That's why I pointed out the 1 liter thing at the beginning. If it had been per 2 liters, then I would have had to have divided that. So if it doesn't directly give you the concentration, if it tells you how many moles it is, it's going to tell you the volume, and make sure you pay attention to that, because if it had been 2 liters, I would need to use half those numbers, okay? All right, so anyway, I plugged those in. This is a really easy calculation to start us off with, and so we should get 0.53. The other thing that sometimes bothers students that really like to be particular, especially my engineering students, you know who you are, notice that it's molar, 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 so only 2 of those molars. But by definition, KCs don't have any units, so you just have to ignore that. Sorry. Okay? All right. So there's your practice. You still got PCl5 and PCl3s. So just, you know, look through those, make sure that you can do that and get the same answer as the workbook's got. All right, now, that was if you're given all concentrations. So you might want to write that, or just, you know, highlight it or something so that you remember that, because if you're given all the concentrations, you just plug it in, okay? There is an example, and I'm going to show you how to do it. So you really get the for more practice on this before, well, wait, no, I'm lying. There it is. All right. So you have the all concentrations. If you're given one with the initial, an initial concentration and an equilibrium concentration, by using the balanced chemical equation, you can figure out the concentrations of everything else using the ice baby ice table. I stands for initial, C stands for change, E stands for equilibrium, and these are all concentrations of your reactants and products as the reaction is occurring and as this change is occurring. Okay, so this is a case where you had the initial and final concentrations. So look, you got the initial concentrations of all of these. It says how much you have. Now, it didn't tell me I had 0 of CH3OH, but I know it's 0 because if I hadn't started the reaction yet, all I've got is reactants, because I'm going to put those reactants together to make the product. So I ain't got no product before I start mixing these things together and reacting them. So you're always going to start with 0 product unless it tells you otherwise. Okay? All right. So this is CO plus 2 H2s gives you CH3OH, and that is a 1 in front of that, lest you be concerned. And so the reaction mixture is at 780 degrees C. Whoa, that's hot. At the concentration of the CO is 0.5 molar. The H2 is 1 molar. And this is molar this time, so you can just write them straight in. At equilibrium, the CO concentration is 0.15 molar. So what I do is I set up this ice table. Okay, now you'll have to just do one, okay, and just do I, C, E, kind of like that, and make your own table, okay? But when you're first doing it, you know, I'll have some out here for you to use. All right, so what I did was kind of like I did under my reaction before, except I just wrote the players in here. I had 0.5 molar of CO, I had 1 molar of H2, and I'm starting out with 0 products. The other thing it tells me is at equilibrium, I have 0.15 molar, and these are all molar. Okay. All right, so this is where I asked myself, what's the change between 0.5 and 0.15? What's the change between 0.5 and 0.15? Well, that goes down 0.35. So it goes down, which is negative 0.35. Everybody with me? Okay, because it told me I started out with 0.5 molar and I ended up with 0.15 molar at equilibrium. So the change was that I used up 0.35 molar of CO. So now I'm going to look at my H2 and I'm going to see if I can figure out from that change, because it's stoichiometric, okay, so it's a 1 to 2 to 1. Yeah? All right. So one thing I could do is I could go ahead and look over here at the product, because this is 1 to 1. So 1 to 1 means if it went down 0.35, the other one was going to go up 0.35, because that's stoichiometric. The hydrogen, however, is 2. Okay, so if I go down 0.35 in concentration of CO, I'm going to go down in concentration 2 times 0.35 for the hydrogen, because it's a 2. And I even write that up here sometimes to remind myself of what that ratio is. So then if I subtract 1 from 2 times 0.35, which is 0.7, I'm going to get 0.30 molar. And in this one, I'm going to have 0.35 molar. And I have now got all the concentrations at equilibrium at this temperature. So very easily, to solve for Kc, I now know what those are. So the product, which is 0.35 molar, is going to be divided by 0.15 molar times 0.3 molar what? Squared, because it has a coefficient, right? So this was, I should have written this at the beginning, I guess, CH3OH divided by CO times H2 squared. Make sense? So all I was doing was I was using my brain to figure out this concentration, which was easy because it was just, I knew that I had to decrease by 0.35 to get 0.15. Then I look and see how that stoichiometrically predicts what the concentrations are of the rest of them using the balanced chemical equation. So the CH3OH goes up 0.35. The H2 goes down 2 times that, because there's 2 moles of H2 for every 1 mole of CO. Therefore, there's 2 moles of change for every 1 mole of change in CO. All right, and so when you get that, and if you put it in your calculator correctly, you're going to get a 26. All right, and so I look at that and I say, oh, that's very product favored. Very product favored, because that's a big number. Okay. And there is your practice. So this talk goes back to the example that we did just previously, except it's doing it at a different temperature, and so you're getting different numbers. And so it's going to be worked exactly the same way. You're going to do an ice table with your CO and your H2 and your CH3OH, and then you're going to put your concentrations in there, which ones are initial, which one is at equilibrium, okay? And then you can go from there, okay? You can do it. I know you can. All right. Remember, this is when you have the initial and the final and a final concentration. Even more practice, because that's what I'm about. Okay, so that's how we're doing. So remember, we did, if you have all equilibrium concentrations, you can calculate your Kc. You can calculate your Kc if you're given initial concentrations of your reactants and one final concentration at equilibrium. And it could be any of them. It could even be the product, which is that for more practice I told you just then. So, all right, cool beans. So that is the end of part 3.